So good morning. I see there are already 2 people participating. Can you hear me? Just to check briefly. Okay. Can someone of you, Valentina or Andre, could you tell me whether you can hear me well? Okay, thank you. So, good morning. I would suggest we wait a little bit because we should have more participants than, well, before. People that I see that are on the Excel list, and I welcome Priya, one of our PhD students. But let's see. So we have 23 registered participants, and so 4 is only a very small participation quote. So let's see, while we wait, whether more participants join us. Perhaps we can do just a little round of introduction. And perhaps maybe if that is possible for you for now, just for the introduction, if you can turn off your camera so that turn on your camera so that we can see the faces. And I see Andrei Garoshko from, and I have the list here of the participants. I just saw you. So
from Russia.
From Russia, yes. Yeah, that I see. Let's see. I thought I had seen your name. So you are from which institution, Andrei?
Yes. Scientific worker I am.
Okay. And you are, I think you are from Krasnoyarsk, is that right?
Yes.
Okay, very nice. And then we have here Natalia Telnova. And I see you are from the Center po Problemami Ekologii I Produktivnosti, Lesov, so from Moscow. And I see some further people here. If you can just turn on your camera just for a short introduction. If that is possible for you, but if not, then no, here from my list, I see also Valerie Avdenyuk, also from Krasnoyarsk, Valentina Zhukova, looking at my list. Zhukova, also from Krasnoyarsk. And Vitaly Tuboltsev, also from Krasnoyarsk. Okay, so Igor, from which institution are you? I cannot find you here on my participant list. Igor? It would be nice to know which institutions participate here in this course. So, possibly I do not have everybody on my list, so I just note down the names. Okay, I see Alina Nikitina from Moscow, Russian Academy of Science. Well, and of course, good morning, Priya, to you.
Good morning.
Good morning, as a PhD student from our department. Okay, good. So yes, yeah, thanks for the chat information. So Natalia Tilnova, just yes, I see you on my list. Thank you for your chat, and other people are saying here hello in the chat. That's fine. So the only person I cannot find here is, and he has also not reacted on the chat, Igor. So from where are you? If you could type that in the chat or just tell us. Okay, so well, it's 10 past, so there's more people coming. Okay, maybe just wait a little bit. I see that name I saw before. So let's say Dr. Utra Irina Gette from Krasnoyarsk also, Sibirski Federalny Universität. Very nice. Okay, and maybe now it's 4, 6, 8 of 23 registered participants. That's still not really a good participation yet. Okay, but possibly, yeah, we should start. So you should be seeing my screen already. Is that right, Priya?
Yeah.
Okay, good. So unfortunately, I don't have a screen here where I could see. Maybe I can later organize that better. I have two screens, but right now, so I have to put your cameras. You can turn your cameras off now, and if you have any questions, then please. Just talk, or I will try to follow up on the chat, but I'm not always paying attention to the chat, which is well hidden below. So the best is if you really just speak up if there is an immediate question. Well, so welcome everybody to a course, a 4-day course on SAR remote sensing. And I will structure it that way because we're listening 3 hours. Nobody can do that. Yeah. We need some breaks. So I thought to give about 45 or 50-minute lecture. And then we have a 10 or 15-minute break. So it's like 3 different sessions. Also, you have all access to the English material and the Russian material. Well, I do understand some Russian, but I'm absolutely not fluent. So I will talk using my English slides. I will try to talk slowly. And I would suggest that if this is possible for you, that you either have printouts lying next to you with the Russian slides, or you look on a different screen, perhaps on the Russian slides, if you have problems with the English language. But I will try to speak slowly. And also, if you have questions, I mean, we can try. Again, my Russian was quite good about 10 years ago, or rather almost 20 years ago. But we could try that you talk in Russian, and maybe I repeat then in English what I understand. So it's more important that you participate if you have questions. In whatever language, and we take the time to exchange, then to move on if you didn't understand something. So also from the participant list, I saw that you all have, or most of you have some background in remote sensing or GIS. I didn't see anybody having any background in radar, so we'll see. But if you have some background, I hope there's still some new material for you as well. So briefly to introduce myself, I'm leading the Department for Earth Observation here at the University in Jena. And this material is based on lectures that we give here at the university on radar remote sensing, and many, many projects that we have performed in the last 20 years on applying radar remote sensing. So the second name you see listed here, Christian Thiel, has been working with me for about 15 years before he left to DLR, to the German Aerospace Center, where he is now responsible for citizen science aspects of data science. So he is the second author here on the first slide, but as a matter of fact, there are many, many more people that have been contributing from our projects and from the department, but this would fill the list too much. So we rather stand for our working groups. So that's the acknowledgement I have to give in advance. Okay, so with this, is there any questions from your side? Otherwise, I would start, and I saw we have another new person entering here our group. And I see here, so we still have two people. I don't know which institutions they represent. So Igor, again, if you could write in the chat where you are from. And then I'm trying to find Sergey Im. You're on my list, and I don't see any Sergey. So perhaps, Sergey, please, if you could also write in the chat which institution you represent, so just to get a little overview who is participating now. Oh, and also I should inform you that I should already going on. Yeah, the session is being taped so that you have all access to the lecture later for your information. Good. So with this, now it's more than 15 minutes later than we have said that we start this lecture, and I will go on. Okay. So again, today we go through the basics, which are necessary to understand what's following in the next 3 days, and especially in the afternoons for the practicals. And so we are talking about first the physical principles, then geometric particularities of SAR data, and I will also introduce what SAR means. Then we will look into different backscatter mechanisms, SAR missions, that you get an overview. And then finally, for today, advantages of SAR and what is phase and where does speckle come from. Very typical radar phenomena. And especially the concept of phase is needed when we go into interferometry. Okay, so part one, microwaves and active remote sensing. Again, I think most of you have a remote sensing background, so you know what remote sensing stands for. It means detecting something on the Earth's surface without being in direct contact. So that is the definition of remote sensing. Well, remote sensing is also in a way a more technical term, and so when we talk about applications, then we rather use the term Earth observation. Because that is what we are increasingly doing, and not doing a technical process of a small part of the land surface, but we rather observe now, monitor processes on the Earth. So the source of remote sensing is always electromagnetic energy, and in many applications, the source is the sun. And then what we measure is the interaction with the object. And even our eyes are remote sensing sensors working in the visible wavelengths. And we even have two eyes, so we are capable of doing stereoscopy. So we can detect where something is, we can estimate the distance, we can see three-dimensional objects. And this is all possible because we have two eyes. And that is, of course, the same concept that is then being used in interferometry. So again, then we would use two radar sensors or two radar acquisitions to perform something like a radar stereoscopy. But what we observe is, of course, very much dependent on our sensors, in this case, our eyes. And what we see is what is being radiated or reflected or backscattered, as we call it in radar remote sensing, from the surface. So we have to be very aware that this, first of all, we have to know what is the source, what is the energy that we can observe. Then what we are interested in is the interaction with the object. And what we see is very much dependent on our sensors and on the geometry. And of course, as a human being, the interpretation that we do is based on our eyes. So here we would immediately observe, okay, it's a green tree, it looks healthy, it's approximately 5 meters high. So this is all cognitional work in our brains. But obviously, again, you see that in this process, there's many pieces involved. Again, the source, the object, the interaction with the object, the sensors, and the cognitive part. And this is all true, of course, for radar as well. Now, instead of looking with our eyes, we can employ satellites like SPOT or Landsat or Sentinels. So then we interpret, for example, the greenness of a leaf as a function of the amount of chlorophyll, which absorbs the energy that is needed for photosynthesis. So now we are going into, we call this greenness, but what we sense is an interaction of the electromagnetic wave and a specific band in that electromagnetic spectrum with the surface. So we see here that this process is dependent on how the sensor is constructed, the technical basis, and it is also dependent on our algorithms that we apply. And then we give what we see a meaning, we call it greenness. Now with radar, this becomes, of course, more complicated because we see very different things. Centered in the camera. So with radar remote sensing, our source of energy is an active sensor emitting pulses using microwave frequencies or microwave wavelengths. Of course, there are other active sensors such as LiDAR that would use LiDAR standing for light detection and ranging, that would use shorter wavelengths, usually near infrared, again, to actively send out energy and then receive what is being reflected or backscattered. So looking at the differences of an optical sensor and a radar sensor is principally that an optical sensor uses the reflectances in the visible or near infrared. It possibly also, if it has a radiometer on board, it can also measure emissions. And well, here it says, well, there's also discrimination between non-imaging or imaging sensors, but let's stick with the imaging sensors because that is what this course is about, imaging sensors. And you can see here is the word radiometer is listed twice. As a matter of fact, we should be listed here also because there is actually an imaging microwave radiometers are available on satellites, but they have very, very coarse geometric resolution. So in this class, we focus on, here you see synthetic aperture radar. This is the, this what is behind the abbreviation SAR, and we will briefly talk about what this means. What means synthetic aperture radar? Why are we using this term? And here you see another technical term, real aperture radar, and you will also learn the difference between real aperture and synthetic aperture radar. But now that we're using the word radar, I would also, for those who do not know what the abbreviation stands for, just go into this short term. Radar stands for radio detection and ranging. Radio detection and ranging. So what does this mean? A radio stands for the wavelengths that are being used, the radio wavelengths. So that is sometimes a problem in radar. We are using wavelengths that are also used in communication, such as radio stations. There you have the radio again. And also in telecommunications. So sometimes we actually see artifacts on our images that come from using such long wavelengths. So radio detection, meaning we are detecting a signal, and ranging, range is the English word for measuring a distance, the range. Again, some of you know the term LiDAR, which stands for light detection and ranging. So you have again the D, A, and R, detection and ranging. So, and again, the biggest difference, of course, is what we're detecting is the so-called backscatter that is coming back to our radar antenna. This satellite here is one famous satellite, SAR X. It has a twin sister, the Tandem X, and with this, the digital elevation model of our planet is being generated. And yeah, so another difference, like SAR X, you see here is the solar panel is oriented towards the sun to get continuously enough energy. We have a communication antenna. This is this little thing here that is sending the data to the Earth, to a receiving station or to another communication satellite. And then what you cannot see here very well is another, it's called a microstrip antenna. That is the antenna that is actually producing the signals. So the radar antenna, it's a long panel-like technology. And you already here, I can refer to some of the aspects that are so important with radar. We always look from the side. So the geometry of our images is a bit strange. We always look from the side. Here, to have the image really correctly, we should have put the optical satellite in a nadir position. So usually with an optical satellite, you receive reflectances in a nadir viewing angle. That is also a big difference, but we come to that later. Okay, so what is the difference between passive and active remote sensing systems? Well, passive remote sensing systems, like most of the optical ones, they detect reflections or emissions. Well, mostly these sensors work in the visible and near or middle infrared regions of the electromagnetic spectrum. So, and in the thermal infrared, it would be emissions of the surface itself. But we all know, obviously, I mean, a warming process is triggered by incoming shortwave radiation. So there is obviously an interaction, which is the basis of the greenhouse process and climate change processes. Yeah, incoming shortwave radiation heating up the planet, which is then emitting thermal infrared radiation in a wavelength range where we change the emission capabilities by our what's called the greenhouse gases, like CO2, carbon dioxide. Okay, this is that. So that optical remote sensing here is covering very different physical processes on the surface than what we observe with our radar systems. So we are also detecting reflected responses, but now we are detecting responses from artificially generated energy, again in a certain wavelength range, but now for radar in radio wavelengths. Okay, and then we have the same process. Well, the energy is transmitted from the remote sensing platform. It's not the sun as the active part, but the sensor itself. And we are measuring what is being returned from the Earth's surface. Well, we saw that image before, but let's look at the electromagnetic spectrum, which I would hope most of you are have knowledge here, but let's repeat this just briefly. Okay, in the optical range, as explained before, we are dependent on the sun, on the energy the sun is emitting, the sun having a temperature of 6,000 Kelvin. Those of you who have some physical background know about the relation, the black body laws. So a black body with a temperature of 6,000 Kelvin emits radiation in a certain wavelength range, which is a range we call the visible wavelength range because our eyes adopted with life on this available energy. So what you're seeing here, and this is important now for our radar techniques, these gray shades show where the atmosphere is not transmitting energy. So again, in optical remote sensing, we know, fortunately, when we go towards the very aggressive ultraviolet wavelengths, fortunately, the atmosphere is not transmittable for these wavelengths. And well, here the ozone obviously is the molecule that hinders this transmission. And again, totally different topic on ozone protecting us from the ultraviolet. Then we have a large, what we call an atmospheric window in the optical wavelengths, but also this is true for the near-infrared and actually several near-infrared ranges. So we have very specific atmospheric windows where the optical sensors work, and in between we have no transmission, and this is all dependent on water and different greenhouse gases, so like CO2. Now, important for us is, of course, the range that we see here, the Earth having a temperature of 300 Kelvin and emitting in a wavelength range of about 10 micrometers. And this is where the thermal scanners come in. So this is thermal energy, and we see there are large parts of non-transmitting wavelengths, and this is what keeps us nice and warm on our planet. But responsible here are the trace gases, the so-called greenhouse gases, and the humans are changing this composition, and thus we are changing the thermal conditions on our planet. But again, this is that's all climate change. Now we move on, and also please observe there is less and less energy coming in from the sun. And there is actually also microwave energy, natural microwave energy from space coming on our planet, but it has very, very low energies. So that is what we measure when we're using passive microwave sensors. We are measuring microwave emissions. It almost sounds miraculous, but we're measuring microwave emissions. Okay, but our focus is on active systems. And we see here at a certain wavelength, we say the atmosphere becomes transparent, but it only becomes transparent because the wavelengths are getting too long to be stopped by anything in the atmosphere, whether it's water molecules or it's aerosols. Or well, not even no trace gas would hinder any transmission of a wavelength longer than a millimeter. So in the wavelength range of a few centimeters, you can see the atmosphere becomes transparent, just because the wavelength is getting too long. Now, here's some interesting little features. These are, this is also the microwave spectrum in the millimeter range. So the atmosphere is not fully transparent, but there is some transmissivity. And these wavelength ranges are used in radar, for example, for the weather predictions, cloud radar. They are looking into the atmosphere specifically to measure the interaction with how many, especially water molecules, are responsible here. So what is the water vapor amount in the atmosphere? This can be nicely measured with these kind of wavelengths. So you could see this also when you look into microwave remote sensing manuals. Okay. Yeah, the wavelengths we are using, we come to that later, are here in the range somewhere between a centimeter and a meter as a very rough description. Okay, so this is very important, and this, of course, is a big advantage if you want to monitor, you don't want to be disturbed by clouds, then radar remote sensing is a good tool. We will look into these frequencies just in a bit. Okay, now I'm just showing it here where these different frequency ranges belong. So, and now this is always very confusing to beginners of radar remote sensing, but that was the purpose of these little letters. I mean, radar obviously comes from military developments because of several advantages I will mention later again. Well, obviously, being able to have an own illumination source, so you can monitor day and night. Also, what I mentioned, you're looking to the side of your carrier of that sensor, which means you do not have to fly over the territory, for example, to measure something if you do airborne remote sensing with radar sensors. So that's another advantage. And a further advantage is that using microwaves, you have a very strong interaction with metallic surfaces. So again, it's for military applications an advantage. So the history of radar really goes back to developments in the Second and after the Second World War. But as you can see with Sentinel-1A and Sentinel-1B, we are now in an operational geoscientific application of radar. So, okay, I have been saying this because these letters here, they were developed as military codes. There is no meaning behind an X-band or a C-band or S-band or L-band or P-band. These are letters coming way back from almost 100 years ago, from not 80, 70 years ago, from military codes. So as a radar student, you just have to learn the letters. They have been kept, well, some of our students, they say like X-band, maybe it's extra short. This is a wavelength we use a lot. The Terra-SAR X that you just saw, the satellite uses X-band. Now the Sentinels, which you may be already using, Sentinel-1 is C-band. And this is a C-band, that's like in the Landsat sensor for well, free radar image applications. C-band is the working horse, as we say. Yeah? C-band is the one where we have historical data going back to 1991. Yeah? So we have now 30 years of C-band time series, which is excellent. And of course, now with Sentinel-1, we are exploring this wavelength. C-band is very important. S-band would be very important. Almaz, a Russian sensor, used S-band. Unfortunately, it didn't work very long, just a few weeks. But now I think the British and UK is a new satellite using S-band. Another important one, because again, we have a lot of free data, is this wavelength, L-band, and maybe like X for extra short and L for long. But again, this is code, so you just have to learn the abbreviations. L-band is being used by Japanese satellite sensors, a very, very important wavelength. You will learn about this. And I think next year already, NASA will launch together with ISRO, the Indian Space Agency, the SAR sensor, an L-band sensor. We are all very, very happy and excited about getting these, again, cost-free data in L-band. And then there's an interesting development. Now here you see wavelengths. We are going, the P-band range goes up to 120 centimeters over 1 meter. Is P-band, and the European Space Agency, ESA, is launching a satellite which is called biomass. It's just called biomass, the satellite. And why? Because it measures biomass, forest biomass. And this is a P-band sensor. First time such a sensor will fly in space. So you just have to learn these letters, because I will be using them and Misha will be using them all the time in the practical. So you see, and you see here that these codes are covering ranges of wavelengths. So there is not one wavelength which is P-band or one wavelength that's L-band. L-band, as you see here, it's covering a range from 15 to 60 centimeters. And again, that is, we still call it an L-band, whether it's a Japanese sensor or it's a US sensor, but they may have a different, what we say, center frequency. They may differ in the exact wavelengths. And that's, again, it's a little bit, how to say, well, with radar, the wavelengths are so long, we don't really worry about the exact wavelength. We just say we are using an L-band sensor. Now, when we later go to interferometry, exact wavelengths become important, but here in the applications, we just say X-band or C-band, or possibly S-band or L-band, P-band. And then, for example, again, what would be the house numbers for you? They just take like the middle, for an X-band. If you remember, it's about 3 centimeters. Then you are good. Just as a house number again, to remember. And for C-band, it would be 5 centimeters. Of course, you can remember exact, but it's good if you remember these house numbers, because if we look later on images, then you should remember that if I just use this pen here, then a radar sees or detects objects in the size of its wavelength. So if you're using an X-band sensor, 3 centimeters, so it's about this. You all have pens, you take a measuring rod, and so 3 centimeters. Okay, that is the size of the wavelength, and with an X-band sensor, we will detect things at this wavelength, at this size. Now going to C-band, 5 centimeters, just a little bit more. The objects must be larger. Now, if you think of this jump to the L-band, because this is other examples here, so the middle would be somewhere by 40 centimeters, but actually you should, like 30 centimeters is a good, just again, as a house number to remember the size. And well, yeah, this is too short for 30 centimeters. It's 20. Well, let's say this pen is about 20 centimeters long. Our L-band sensors are 23 centimeters. So you see, I mean, it's just a very different dimension of objects that can be detected. And maybe you already can envisage that an L-band sensor doesn't care about small objects of 2, 3, 5 centimeters. A long wavelength like this would just penetrate through vegetation, for example. That is why long wavelengths are used to measure forest densities, because here the backscatter comes from from the forest stem. It's not much interaction with the leaves. And that is the reason why this new P-band satellite being launched, it's envisaged for 23, I think it probably will rather be 24 or 25. So another 2, 3, 4 years until this very exciting biomass satellite is being launched. And again, why? I mean, now we're talking, I think this has a center wavelength of about 70 or 74 centimeters, so almost a meter, yeah, a very, very long wavelength, which penetrates even in the tropical forest through the canopy, and then you get backscatter from the stems. So again, I think it's nice to have here also the colors kind of, and here these shorter wavelength, this is where we are in the, going to the millimeter range and Ka, Ku bands. So these are being more used for atmospheric applications, because here we have some problems with the atmosphere due to the water molecules. Okay, please. Yeah, now we will use these abbreviations: X-band 3 centimeters, just as a house number. C-band about 5 centimeters, and L-band up to 30 centimeters. Again, just to have a number in your memory. And well, there is a connection between wavelength and frequency, and we will come to that. Yeah, and this is something that happens if you read about radar, or us talking about radar, that we also talk in frequencies, in gigahertz. And then the important frequencies, again, is like middle numbers. The C-band makes it a bit easy. If you remember the house number, 5 centimeters wavelength, and again, a house number as a frequency, it's 5 gigahertz. So C-band has a 5 centimeter wavelength and 5 gigahertz. Now, if the wavelength gets shorter, the frequency increases because of the constant velocity of light concept we come to. So if the wavelength gets shorter, the frequency increases, and here we have our 3 centimeter wavelength, and we would have 10 gigahertz. 10 gigahertz, again, as a house number, just to have the dimensions makes it easier for your brain to remember. So 3 centimeters and 10 gigahertz. Okay, if we move to L-band, because X, C, and L are the important frequencies for us. Again, as a house number, we said like 30 centimeters, and then we have 1 gigahertz. And I give you, that's why I give you these house numbers, yeah, just to, it's easier to remember. 30 centimeters, 1 gigahertz, and here we had 3 centimeters and 10 gigahertz. And for C-band, 5 centimeters and 5 gigahertz. Okay, enough about this, but this is important because I will be using X or C or L, and I hope you scribbled this down, you wrote this down somewhere. So when I say C-band, you remember 5 centimeters, or L-band 30 centimeters. Okay, now, so here again, the frequencies are highlighted that we use most. The concept of velocity of light. Now we have a constant c, 3 times 10 to the 8th meter per second. So because we're having here a constant, our wavelength lambda is directly coupled with the nu, the frequency. That's the term for frequency. So now it becomes mathematically easier to understand that if you increase the length of your wavelength, then obviously your frequency goes down. And if you decrease the wavelength, then your frequency goes up. Yeah? So this was the connection with, if I would ask you now, what was it again? X-band, X-band, short wavelength, 3 centimeters, and here 10 gigahertz. And what was L-band, 30 centimeter wavelength, and it was here 1 gigahertz. There's the connection. Yeah, what is a wavelength? Well, an electromagnetic wave is described within an electric field and a magnetic field. We are interested here in the electric field. This is defined by the amplitude, so how much power is in that radar signal. The wavelength is defined as a distance between successive wave peaks. Okay, I think that's all what's needed for now. Maybe just these lines here, these vertical lines, so they indicate the amplitude. So again, this is the power of the signal. So the amplitude is higher, the more power is being sent out by the radar sensor. And if we think of the backscattered returns, then again, the larger the amplitude means the larger that backscatter from a certain surface. Okay, let's see what comes next. We're going. So this would be important concepts now. See any questions up to this point? And again, you can talk Russian. I can try to understand. I would answer in English though. Or you talk English, of course, or you write it in the chat, whatever you feel comfortable with. And I see we have 13 participants now, which is still just a bit more than the Priya is from my department, so it's just half of all registered participants, which is of course sad. Okay, so no questions to this point. Then I suggest we continue for another 10 minutes and then we make a short break, about 10-minute break. Continue. Okay, there's something in the chat. No questions. Okay, all right. Good. Then let's go back to the presentation. So, well, active radar interaction with the object, we talked about this, so what the radar measures is the echo. And just a visual example, if you shout in a canyon to a canyon wall, you also hear your returned echo. Okay. Characteristics: no sunlight required, no problems due to bad illumination. Well, a problem, especially you know very well in your northern territories, where you obviously, due to the low sun angle, you get interesting sun illumination effects. The shadows that are being included in a pixel become stronger and stronger if we go into northern winter conditions. So, well, this is all can be neglected with radar. Well, it penetrates into or through objects, and almost no problems with clouds or dust, which means you can sense hidden things. We'll come to that. Obviously, this is dependent on the wavelengths that we are using. Okay. I was just thinking, let me just briefly go back once more here. Yeah, I would assume that many of you have a microwave instrument in your kitchens at home. And I just wanted to mention this here. Usually your microwave in the kitchen, look into your instructions, then you can see the wavelength. They often work in well, what we could call C-band, or often also S-band. So they may have a frequency of 3 gigahertz, for example. Now check your microwave instructions, and it's just a nice analogy to always think of what's happening in your microwave in your kitchen. Because from that analogy, you already know what the radar backscatter, where the radar backscatter comes from. It comes from water molecules. So the radar wave, or these wavelengths here, they interact with water molecules, so they bring them into rotation, and that is what makes your chicken or your coffee hot. And if it's a frozen chicken, for example, that you put in your microwave, then the water is in a crystalline structure. And so it's also easy for the radar wavelength to penetrate through that crystallic structure. And everywhere where it hits on a free water molecule, it brings it into rotation, and this rotational energy changes into warming up the material. That's why you should also let your food, if you microwave it, just let it stand for a while, so that from the rotating water molecules, the warmth is being spread through the tissue of your chicken, for example. So it's just a remark that I wanted to mention when we talk about the wavelengths, and here now the dielectric characteristics. That's what radar is. Well, it's interacting with dielectric characteristics, as it says here. But what is the dielectric? It's water. It's water molecules, or metallic objects that have a high dielectric conductivity. Okay, but we are obviously interested in water. Now, and this is why here it says almost no problems. If the clouds get really too thick, if there's too much water in the cloud, then the shorter wavelengths, of course, they run into trouble, and we will see some examples. But usually the wavelengths we use, we can say they penetrate through the atmosphere, and they even penetrate into a vegetation canopy or even into soil. So the magnitude and the characteristics of backscatter, so this is a term you should remember. We don't call it reflectances, what we measure, we call it backscatter, is dependent on the geometric and the dielectric properties of the objects. So, and the geometry, again, this has to do with this long wavelength. We have to consider the roughness, so the roughness of the surface, but also, let's say, the geometric structure of vegetation, for example. So this is all things you will learn in the next couple of slides. Okay. Very, very famous example is this one. It's one of the first ones being published, showing the power of radar. Here you see a Landsat thematic mapper image of a oasis in Egypt. And some image processing has been done here. So you see some geologic features, you see the sand, you see dunes, different mineralogic surfaces possibly. And this is what has been mapped with a famous shuttle mission, SAR in 1994, showing how radar wavelengths penetrate through this hyper-arid sand layer on top of old, actually here these are old river systems, former prehistoric river systems, now being covered by the sand layer. So this was like a revelation. Revelation, is that the word? Or you can also say revolution. In the 90s, seeing the power of these very long wavelengths being able to penetrate, and it has later been measured up to several meters through a very, very dry sand surface. So the answer behind this as a miracle is, there's no water in this sand layer, and sand is still a volume that is, gives enough free space for the radar wavelengths to penetrate. The radar is kind of searching either for a very, very dense layer. This is what is happening here, the sediment of these buried riverbeds. This is fine sediment in the riverbeds. This is forming now a subsurface that is causing the respective backscatter mechanisms, but this is due to the very fine sediment. And in between, these are probably rock surfaces in between these old riverbeds, and everything is being covered now by dry sand, and the longer wavelengths just penetrate, and what we see is what's below. Now, SAR is a term I may be using also sometimes because I had the pleasure to be part of this shuttle campaign in 1994 from the German Space Agency. So SAR stands for Shuttle Imaging Radar, and C was the third mission from NASA's side. So there was a SAR A and a SAR B and then SAR C. And when in 1994 this shuttle mission took place, the German Space Agency cooperated with NASA, and we brought an X-band. Yeah, remember the X-band. So here is a bit confusing. The C-band is not standing for C frequency or for the code of a C-band. It stands for the third shuttle mission, and here the X-band is indeed for the short wavelength, and SAR, again, the synthetic aperture radar. We will talk later why this funny term, yeah, SAR, synthetic aperture radar. And again, you will hear me say radar and SAR. I use it the same way because all radars that we use are SAR systems now. They are all using what is called synthetic aperture radar. So SAR is the same like radar. Don't get confused if I say this radar or SAR for the same thing. Okay. So X-band SAR was the German contribution here to this mission. Okay, this was the end. Yeah, that's if you talk about this penetration capability, this is at the just another example here of a comparison of ERS-1 as the first European radar satellite. It was launched in 1991. So here's just an image at the 4th of July at 10 a.m. and a Landsat 5 image on the same day, just 45 minutes earlier. And so the comparison, and you can find these kind of comparisons a lot in the literature of having clouds over an optical image, and obviously the radar looks through. But well, this image doesn't look very nice. And that is the reason why not many people have been using radar, because principally a single radar image is not really nice to look at because of all these funny influences we will talk about later. But now we are, of course, in a different decade with Sentinel-1. But also radar, and this is an example. I think actually this is from one of the shuttle campaign, XR. Yeah, this is of this shuttle campaign in 1994, but this obviously is processed in 95. So what you see here is using the X-band, the short wavelength of about 3 centimeters. If you look into the tropics, and here we're looking at Senha Madureira in Brazil, then clouds start to become a problem, and you get some backscatter, and you get even something what we call a radar shadow here in that image. But this only happens over tropical regions and using shorter wavelengths. So this is something with Sentinel-1. It depends again now what this tropical storm, how many water molecules are here hidden in that tropical storm. Then you may have some interaction, and you would see that as such a fuzzy appearance in your images. So with X-band and tropics, problems with C-band, not so much, but you have to be careful of it. Okay, and with this, I don't know what's happening here on this is just a summary of what I've been talking. And I would just say, let's do a 10-minute break and let's come back at in 10 minutes, a quarter past, whatever your hour is. And I just leave this as a summary of what has been said until now. So I would not assume, because this was just examples. Any more questions? No. Okay, so let's meet again in 10 minutes. And thank you for your attention so far. Okay, so yeah, welcome back. And we continue with the next 45 minutes of our presentation. And for those who came in late, so just for your information, I'm obviously talking English and using the English slides, and I would suggest that you print out or have the Russian slides available to you if you have any questions with respect to the English terms, then you can always look it up on your Russian slides. So again, I'm happy to see we have here 13, but actually we have 11 participants of 23 registered. That is, now, well, I wonder why. What has happened to the other participants? Anyways, let's move on. I'm very happy about those who are here participating and representing many famous institutions in Russia. And yeah, it's too bad. I have been several times to Krasnoyarsk and obviously Moscow too, and also to many of your organizations. And it would be a great pleasure to be in Siberia right now. I would love to be there, but as we know, we have a pandemic going on. And so unfortunately, we cannot perform this course in presence. That always makes things easier and nicer and much better to have direct interaction than to talk here on a screen, and you're watching me like television. That sounds very, very different ways. It has some advantages, but I think the disadvantages are bigger. Good. So let's move on with our lecture. We came to this point. So some further examples, just to get in the mood to further details. This type of images of detecting something is very, very famous from radar remote sensing. What you see here is actually oil spills coming in this example here. It comes from oil platforms that are spilling oil on the sea surface. So we are looking at a water surface, and what you can detect here is already wave patterns. So you see there is a wave direction. Obviously, these parallel lines, that there's waves, but we also see something like these plumes on top. So a different texture, which is related either to some upwelling phenomena from below, but it could also be impact of weather conditions on top of the surface. So what it shows is how sensitive the radar signals are to surface roughnesses on a water surface. But saying this, what can be observed here, this is the reason why these oil surfaces are so well visible. The oil flattens the surface. Now the oil sits as a coat, as a coating, as a film on top of that water surface. And it has such a heavy structure that it flattens all the otherwise natural occurrence of roughness out. So it's a very smooth water surface, very smooth. So you can, on this example, you can already learn the first two scattering mechanisms. One is specular reflection, and this is what's happening here. Yeah, the incoming radar signal is being scattered away from the sensor. So specular reflection, it's called. And what you see here is a result of various diffuse scattering mechanisms. So when you have a diffuse scattering on the surface, then you get also backscatter back to the radar antenna, back to the sensor. So this nice texture pattern that we see here of this linear brighter features yeah, or these darker plume-like features. This is all interaction of different roughnesses on the water surface. Okay, so this is lesson number 1, specular reflection, causing dark areas in an image, diffuse scattering on a rough surface, causes various types of strength of the backscatter. So it's very important to remember this. It's a very easy example, but it's very important to remember how drastic the difference is between a smooth and specular backscattering mechanism or various types of diffuse backscattering mechanisms. So lesson number 3 is radar does not penetrate water. Radar does not penetrate water. Water is a perfect conductor, so obviously it has a high dielectric constant. It perfectly conducts electricity. So the incoming radar or the radar pulses hitting the water surface will not penetrate the water volume. So everything what we see here is an interaction of the radar wave with the surface, specular or diffuse reflection. So sometimes you see of shallow water, you see very interesting radar images that almost look like they detect the subsurface, but they don't. It's the interaction of the water material with the subsurface, or with the currents or the wind. Okay, specular reflection, diffuse backscattering, radar is not penetrating water. Yeah, the importance of water can of course also be seen here in these nice examples of irrigated fields, this so-called pivot irrigation systems. And it's just an example of showing how radar is dependent on water or vegetation that is being filled with water. So here in this example, you just see different land use, different crop types, and you even see differences, obviously, in the water content of these in these fields. So you can detect interesting characteristics of the surface with a radar signal, but still we see these images don't look too nice. We have this kind of a salt and pepper effect. It looks very disturbing, and that is what is called speckle, and you will learn about this today, why we have speckle. Okay, well, now this is a different type of image. Now, if you put a radar sensor on an airplane, of course, you can get a much higher geometric resolution. So here we are seeing the result of an image from an airborne system, an airborne SAR system of DLR, the Deutsche, this is the German aerospace establishment. Deutsches Forschungszentrum für Luft- und Raumfahrt, so for aero issues, airborne and space. And this is now, it uses here a term, fully polarimetric. So this is the next characteristic of radar you have to learn. X-band you know already. But now we are looking at a color composite, red, green, and blue, a color composite based on different polarizations. So this is the next abbreviations you have to learn. Very easy. H for horizontal and V for vertical. And HH means the radar wave is being emitted, it swings, I should make this signal now, it swings horizontally to the Earth's surface. So the radar signal is emitted, the pulses swing horizontally to the Earth's surface. And the second letter here, H, means that we also, what is being received is only what has been backscattered in this horizontal plane. So a funny concept, but on the other hand, I always think, if you think of, again, the wavelength that we were talking about, this large wavelengths, and now you have this second term, radar is all about geometry of the surfaces. Now, if you always have to remember, okay, what am I seeing? What's the wavelength I'm using? And what is the polarization? What may be the interaction of a 3 centimeter wavelength or a 5 centimeter wavelength or a 20 or 30 centimeter wavelength? Yeah, with objects that when I observe them in a horizontal plane. So the radar wave is just like a snake, yes, swinging in horizontal plane. And HH means I'm receiving, I'm registering, I'm coding only now backscatter that comes back in that horizontal plane. So I have to make that distinction, HH, or I can determine with some sensors, I'm sending out horizontal, so my waves swing in a horizontal plane, and on the surface, of course, they scatter in all kinds of directions. This polarized wave, the polarization will be changed depending on the geometry of the surface. And well, now I want to receive only what has been what we call depolarized. So what has been changed from the horizontal plane to the vertical plane, and I'm now only detecting what comes back in the vertical geometry. So in VV is then sending out vertical and looking at what comes back in the vertical plane. So in there are some, also this system here, but fully polarimetric means that simultaneously the radar sensor can send out horizontal and vertically polarized radar waves, and it also simultaneously can receive what comes back in a horizontal or in the vertical plane. Now, so these are the geometries. There are no other angles. We have only horizontal and vertical. And there have been experimental sensors that looked at all kinds of other angles, but it gets far too complicated. And the merit, the advantage of looking at other angles was not so big that it has been implemented in any sensor. So all radar images, we have only these geometries, horizontal and vertical. And as a matter of fact, this means we have, if we look into these polarimetric constituents, we would have 4 combinations. Yeah, we have HHVV. So then we have this HV, and now one is missing, which would be very easy VH. Yeah, so we can send out horizontal, receive horizontal. We send out horizontal, we look at the vertical backscatter. We send out vertical, we look at vertical, and the 4th one would be sending out vertical, but receiving the horizontal. And I mean, obviously, our color composite can only represent 3 channels. So this 4th one is missing now in this color composite. But if you think about it, okay, let's introduce another term, a technical term. We call this a co-polarized image, co-polarizations, because it's the same polarization we are looking at, horizontal, HH or VV, we are co-polarized, or we're looking at a cross-polarized image, so HV or VH, sending vertical and receiving horizontal. And now looking at this cross-polarized channel, we are looking at the, again, at that backscatter that has been shifted from one polarization to the other, which means we are now, and this is, dear participants, number 3 of the backscatter mechanisms you have to learn. One was specular, the other one was diffuse, and now we're talking about volume scattering. Now, so this polarization combination here is most sensitive to what is called volume scattering. Now, where do we have volume scattering? This we have in vegetation. The more leaves we have, now imagine your wavelength penetrates into that leaf canopy, and every leaf, which is water-filled, every leaf causes a depolarization of your incoming wave. And if you have such a volume like a plant canopy, it doesn't matter whether you look horizontal or vertical. If it's a volume of many, many leaves, then it doesn't matter whether you go in horizontal or vertical, because there is this, what is called volume scattering. So actually, HV or VH would be similar, almost the same probably. Let's say similar to be on the safe side, but very, very similar, maybe same. Yeah. So it's actually enough if you have HH, VV, and HV or VH, it doesn't matter. Okay, so now we see here, okay, first, well, we come back to polarization later again, but I mean, this is sometimes a problem that somebody working with optical images, yeah, it's hard to understand that now you determine the plane in which a wave swings. Good, so what are we seeing here? I mean, first of all, you see something that makes radar so nice also for geological explorations. Yeah, we have, okay, if you look at that image, you can already determine from where the radar antenna looked on the image. Now just think for 5 seconds, from where did the radar illuminate this area here in Bavaria? From where? So the answer is very, very easy because we have an illumination side. Yeah, we see here some bright areas, or here some bright areas. Here we have a bright area, and we see what we call a radar shadow. It's like if you put an illumination source, a torch or something on the surface, yeah, then you would get a shadow. So here, and this makes for your brain, this makes the image so nice, so textural, because you have everywhere, especially where you have settlements, you always have an illuminated side and a shadow side. Yeah? So you can see the structure of this little town, or here you see the structure very, very well. And the same is true, of course, here for the forest. You have an illuminated side, but also within the forest. Here we see some different patterns in that forest, yeah, that come obviously from the way it has been planted. You see the planting rows, or here you see different age of the forest. This is not as high as the surrounding because we see again an illumination. Here we have a clear cut, there is a shadow. Now we cannot look into that shadow. That's a problem. Yeah, we cannot look into the shadow, but it makes the this picture, or almost say this scene, yeah, very plastic. So, and of course, by the length of the shadow, like in air photo interpretation, you can already estimate the height of that forest also. Now you know from where the airplane was, you know your geometry. So you could already detect something. Yeah, what else? So I think that's the most important principle here for you to learn. Now let's talk about the colors. Now we have, okay, what we see is, okay, there is a lot of green, yeah, especially here in the forest, but I mean, of course, for in any color composite, you know that yourself, where you can change the histograms, and so we have to be a bit careful not knowing exactly what the histogram stretch here possibly was. But we obviously see that, well, the forests appear here in this image greenish, yeah, which means, okay, we have a large contribution from the volume scattering, yeah, which is normal. We have on various of these fields, we also have a more rather greenish look of the fields, which means that obviously this image was taken when there was vegetation. So there was always a volume scattering component. Now, what else can we say? I mean, I don't know exactly where that area was, and unfortunately, there's not even a date when this was taken. But seeing that there is a large green component means that there must have been vegetation on the fields. So, well, we see something else where we have these black areas rather, or dark. Okay, and now we remember from before, yeah, now remember what was dark again? Dark was specular reflection away from the sensor. So also in this image, everything which is dark means, okay, first of all, there's no volume scattering, meaning no vegetation. Also, dark means also the HH, the copolarized channels, underwent specular reflection. So this must be very smooth, especially if we think X-band is only 3 centimeters. Now this must be quite smooth surfaces here. What else? Yeah, then we have some areas here. This one, for example, is like yellowish. Well, in image processing, yellow is green and red causes yellow, which means we have here some volume scattering, but there is mainly contributions from the horizontal backscatter. And this looks like here maybe some harvesting is going through. There is still vegetation standing, or maybe it's just stubble piles of old vegetation. Yeah, there is a volumetric component in this, but obviously no VV returns, so less bluish. Yeah, and so again, I mean, we need, of course, some knowledge of the surface to understand what are the crop types, but as you can see by these colorful image, you could already, using normal image processing classification techniques, yeah, you can segment this image, you can classify the image. This is no big deal. Okay, what else? We see here some like white areas, and only in the very white areas, or the same here from those buildings, at that side, yeah, it means that from obviously all 3 polarizations, we get backscatter because only this causes white. Okay, so and with this type of geometric resolution, I mean, you even see individual trees and the shadow, but for this is not what you would get from a, let's say, in a free and open radar satellite. There may be, again, commercial radar satellites that also go into these kind of decimeter resolution type. Again, and what you obviously can also see that everything that is structured, like the houses, they cause large reflections. So everything human-made, or here that looks like a railroad track, here a road, here a little a river, and possibly here a little channel, a water channel. So everything artificial, because it causes these corners, cause also very high reflections, backscatter, I should rather say, like the one here at the forest edge. And of course, yeah, this makes it a very nice instrument for detecting or mapping any human alteration on the surface. And there's also endeavors. There's, for example, a global urban footprint that has been constructed from radar images, because only with radar urban detection is quite a straightforward process. For those of you who work on urban areas, you know, with optical images, you have always the problem of mixed pixels. So from vegetation and buildings. And an optical image, it's difficult, also special urban types when they become more rural. Yeah, the more vegetation is surrounding your buildings, the more difficult it becomes to map urban areas. Of course, if you have very high resolution images, all kinds of things are possible. But with radar, it turned out that the stability of this pattern, of these very high backscatter returns from buildings, the stability over years is a very nice help to map urbanized areas. So for those of you who are interested in urban, look up the global urban footprint, a global map of settlements. And of course, the change of settlements. Okay, so this is enough, I think, for this image here. This is even a subset. So, well, of course, I mean, this is where there's even a nice viewing of the different parameters. So zooming in, I mean, this almost looks like an air photo now, but again, this is an airborne system with a very high resolution. And what again makes the radar so special is that maybe this is a little tree school. It looks like little trees with shadows. It's the mixture of having an interesting method of measuring the geometry, the structure of the surface. Also looking here into the forest. Yeah, again, it's like an air photo because it has a very high resolution, but the texture is very nicely visible because why? Because of the radar shadow eventually. Yeah, so even different heights of forest, individual trees are nicely detected because of the interaction backscatter and shadow, or smoother surfaces are easily visible. And then the polarization comes in as here the parameter that gives the color. Yeah, so again, if you, but the principle stays the same when we will look at Sentinel-1 images. Yeah, the texture of the surface causes also in your mixed pixel, when we go then to Sentinel-1 has 10 by 10 meter resolution. Yeah, but still these geometric effects cause, well, the backscatter of your pixel. So some, it's just some artifacts here, again, metallic structures. Here you can actually see an electricity pole standing here, very large returns. Also here, this looks like a sewage company. We are clearing the water, and these are metallic rods that go around these pools that clean the water. And they are metallic structures. Yeah? So the metallic feature, of course, gives very large returns. Also here must be some metallic features that cause these very bright spots. Okay, yeah, so this is also already a lot about radar backscatter mechanisms. So, and always remember, if now, of course, we zoom into something where we see a lot of different. Okay, there's something else I would like to mention here. Yeah, using these polarizations now is, of course, helpful to measure even different grassland communities. Why? Because with the polarizations, and here this was an X-band image, so very small wavelength, yeah, there is a very sensitive interaction with the grassland geometry, with the structure. So because of the dependency with the geometry, you see also here the lines in the field. And of course, we have to remember, now if I would draw in a 10 by 10 meter pixels here, yeah, that of course, yeah, we get all the time interaction of the geometry of the surface and its water content. That's always geometry and water content, geometry and water content. And so perhaps you can imagine if you look now into time series, the same as for optical data, yeah, you start to be able to map such, for example, grassland communities. Or here, obviously, we see an old river pattern going through. Not what we saw in the desert image before, but what we see here is the soil type is a different one in this region. And so the vegetation is obviously following a different phenological pattern. And you know that from your large fields as well. Yeah? If you have different soil types, the phenology of your fields will be different. And if you think of precision agriculture, this is then, of course, very helpful to monitor such heterogeneities within the field. And so this is what we are doing here in Thuringia, now using Sentinel-1. Here in Thuringia, we get every 3 days, we get a Sentinel-1 image, either A or B, and we monitor the development of the phenology on the fields. So we cannot see what an optical system sees. Yeah, so we don't have an NDVI Now we have to interpret this time series very differently. What we monitor now is the vegetation, water content, and the phenology with respect to the structure of the vegetation. Now, structure and water content, that's what we are seeing. And always with respect to the size of the wavelength, 3 centimeters, 5 centimeters, maybe in L band, 20 to 30 centimeters, and with the polarization. So always think of the geometric resolution, the frequency you're using, the polarization you have. And that causes this type of interaction. And this is actually a nice example here because this looks already nice, but looking at the subset, again, this is very, very high geometric resolution. But if you think you would overlay here a 10 by 10 meter pixel, then still what makes up the backscatter signal comes from such a background. Also here, nice, probably there's also some grassland area and you see different features, different development of the grassland. Okay, enough of that. This is another image now, also from this airborne image using L-band. So here the, excuse me, I don't know exactly the wavelength, probably something 25 centimeters or our house number 30 centimeters. Okay, and now what we observe first. Okay, let's look at what this is. It's airborne, so it's still relatively high resolution. Now an image from April, an image from June, image from July. Yeah, so things change, of course, over time. But what we see here with the L-band is, well, some features you have already learned. We see little settlements staying as bright patterns, because we have this, what is called corner reflection. We come to that later. It's a specular reflection, but now at the house corner and the soil or the turret, the basement. Now, so from the scattering mechanism, it's a specular reflection, but twice, so it comes back very strongly. This was causing these white backscatter in the towns. Now we see some streets, also they stay white, and this can only be either it's on a dam, but rather this is maybe a little alley with trees along the streets, so they stay white over all three images. Then we have a large spot that is white in all three images. So most possibly like this thing here down here, most possibly this is forest, because it stays stable from April to July, and it is very bright. So the composite is again a polarimetric composite, HH, HV, and VV, same as before. And white areas mean strong backscatter in all three. Okay, what else? But what is obvious here, the agricultural areas look dark, relatively dark. And again, this means for this wavelength now, the L-band with let's just say 25 centimeter wavelength. Now this agricultural area mostly causes specular reflection. Most of the backscatter, because of the very long, the very long wavelength, because of the very long wavelength, is being scattered away. I'm showing this because, well, one thing is what we can observe here, these fields that are developing to white fields. I've looked at them before, they were here very dark. So something is growing here between in that 1 month even, something is growing rapidly to cause now backscatter in all three polarizations, always meaning if the cross polarization is showing an increase, then it means there is volume scattering component. So here's vegetation growing and pretty fast, which does happen. Okay, what else? Yeah, here, well, this pinkish field, of course, causes attention. And well, now we see something that's happening in between and is disappearing. So if such features happen, which appear and disappear, this may be connected to changing the surface roughness. This may be connected to plowing activities. So it's important to have such time series to see what's happening here. Of course, what I said before, something is growing here, maybe something has been growing and has already been harvested. So you have to have some knowledge, of course, of the area, what's the crop practices. But what I also want to show, and this is what sometimes brings people away from radar, but you have to know the features that you see, and they may be helpful in what you want to analyze. So obviously, I mean, here you see some lines that are obviously connected to the plowing activities. So, and over the time, at least here, they start to disappear. So what you're seeing here in mid-April is the plowing activity, and you can, with knowledge about the crop cycles of the area, you could also start mapping regions. So you could develop a crop type map and a crop practicing map, because you can see how the surface changes. And now here these patterns disappear because the vegetation is growing. Okay, so these features in a radar image where you first think, oh, this looks like an artifact and it disturbs my classification. Always think what radar gives you. It gives you the surface structure. It gives you information about geometry. And you may actually be able to develop an algorithm that includes this in your crop type mapping and crop monitoring. I mean, we use radar to monitor because we can look through clouds. Okay, it's just something else that is also important, because you may see such features. Here you see these very disturbing lines in the image. That you kind of, here's like little stars that overlay here your fields. So these are, in such an airborne image, it's less visible in satellite images. You have to have a very high geometric resolution, but these are obviously artifacts that come from metallic objects. So most probably this is a power line going through, so metallic, the electricity towers that give here such strong reflections. And there is a feature up here that I wanted to point out. Here you see it's in reddish colors, this line that goes through. And here it's not so visible, interestingly. Here it becomes visible again. So such a feature, and you see red, meaning it only comes from the horizontally polarized. Again, we're talking here airborne image, and you wouldn't see that in a satellite image really. Is the backscatter that comes from the electricity wires now. And the look direction, now we could also look a bit, do we see here a nice shadow anywhere? It's a bit difficult, you need to zoom in, but the look direction here of the sensor must have been, if I look at here, it's at the forest, we can see it nicely. Here is the illuminated side, and here is the shadow side. So the sensor was looking from the left to the right. And obviously here that power line was more or less parallel to the flight line, which means now the horizontal, the HH co-polarized channel interacted directly, looking parallel to the surface. You had an interaction with the electricity wires. So you're getting this backscatter here, and this is why this feature is reddish. But to see, one thing is the geometry must be exactly like that to get that interaction. It looks like here, because this is airborne, the plane probably, maybe it must have had a little bit of different angle to the power line. So the power line disappears and here it fits again. Again, you need a high geometric resolution to get such features. But it only proves again what radar sees is connected to the dielectric features on your surface, which is either connected to metallic objects, to man-made features. So everywhere where you have a straight corner, or this, like a building and the basement, over the camera, building and basement, or water content of the soil surface or the vegetation. And again, of course, also surface roughness, like we have seen it on the water surface. So in its principle, it all reduces always surface roughness, geometry of that object, and the water content, or again, this the dielectric feature. And always remember the wavelength and the polarization from the sensor side. So we have like 3 components from the surface: roughness, geometry, structure, water content. And from the sensor, we have the wavelength. You've learned that. We talked about the polarization. And the third one from the sensor side is the incidence angle. And we will come to that. No, but you have a good basis already for your radar interpretation, and some further examples showing you, again, now the power. This is an airborne, again, the German Aerospace airborne sensor. Here flying C-band, and L-band, and experimentally the P-band that I introduced in the beginning, about 80 centimeters. This is a house number, 1 meter, 1 meter wavelength. Looking on Indonesia, Kalimantan, and these were preparatory flight campaigns to prepare the P-band satellite. I have also introduced in the beginning the biomass satellite. And so now you start in the tropical rainforest. In the C-band you don't see much. In the L-band also not really, but in P-band you start to see differences in that tropical rainforest. You see roads going through that were not visible before, and also you see different features here in the forest coming up. So in this area. Also, of course, the distinction between forest and here possibly some peatland, so difference between forest and non-forest. Different size of vegetation becomes more is better, easier to be distinguished. So again, always remember the wavelength and the objects you are looking at. And with C-band, this may actually cause difficulties to discriminate between, let's say, a dense marshland with a lot of dense vegetation or regrowth, bushes. If it is very dense, it may look similar, as you can see here. Again, we're looking at a polarimetric color composite, HH, copolarization, HV, cross-polarization, and VV. And it's hard to distinguish something, but the longer the wavelength gets, then, let's say, the relation between the length of the wavelength and the geometries of the surface vegetation become, let's say, more distinguishable. I'm just looking also up here. This is also the differences become a bit more visible because the P-band, of course, with the longer wavelength penetrates. Now here, this vegetation, it's a different type of vegetation, better than here before, than here in the forest. So, just thinking how to explain. I mean, here are now backscatter components. It's more turning yellowish. So we have a larger contribution from HH and HV and less contribution from the VV polarization. There's also a feature becomes now visible that if you look here at the C-band, it's not visible at all. So obviously, something of the underlying surface is now being detected if you go up to this, again, 75, 80 centimeter wavelength. You need that long wavelength to detect features below the vegetation. And here we get an interaction only on the vegetation. Everywhere is dense vegetation, and the C-band therefore sees only the vegetation canopy and not what is below. Now with the L-band, here this feature starts to become visible. So probably, maybe there's some more moist soil below, maybe even standing water, because if it's getting dark, it means, what does dark mean again? The specular reflection, like on that river, the specular reflection starts to rule over diffuse or volume scattering. Dark always means specular reflection. So here specular reflection components come in with a long wavelength. So there is some vegetation, but it is definitely smaller than the surrounding tropical forest. And this border here gets very clearly visible. So this is a nice example for this reason why the European Space Agency puts millions of euros in the development and launch of that P-band satellite in the next 3 years. Again, I think they say 23, but as usual, it probably becomes 24 until the satellite called Biomass will be launched. So again, these P-band images are relatively rare. Not many space agencies fly such P-band airborne systems, but such campaigns were necessary to prepare the satellite mission. Okay, let me see why we look at it. Oh yeah, it's good for the next break. Again, as a nice summary, I just let that here stand. Here it says, okay, where is the backscatter coming from? Again, we're looking at our Terra-SAR X satellite. But of course, this is true for everything, size, shape, orientation. So until now, because of course it's difficult to discriminate here, but that's why I rather call it like the geometry of the surface, whether it's vegetation or it's anthropogenic structures or it's geologic surfaces, the geometry of the surface, the dielectric properties, which is the water content, and then what is actually missing here is the surface roughness that comes in. These are the three components that are important that change the backscatter. Okay, and with this we go then in the last part to the geometric particularities. This is now that you've got a basis on what radar backscatter is, we go into the details of image construction. I would say again, just to refresh your mind for the last our 10-minute break. And we meet again at 1:15. If you do not have any questions right now, if anybody wants to speak up, I see nothing in the chat. Please either write or say, and again, don't be shy, you can ask in Russian. I will try to understand. Yeah, Priya, I see your hand. Please, Priya.
Yeah, I have a question on that oil spill slide, what you have shown.
Yeah.
What are those white structures? Is that a ship or something? Or
it's an oil platform. These are oil platforms in the ocean.
okay.
oil platforms. So, I mean, you can, it's like a ship. Yeah, you're right. It's a metallic structure, but, you know, oil rigs, I think they're called oil rigs or oil platforms, oil islands. I mean, these metallic structures in the oceans. And since they drill oil, yeah, sometimes they also spill oils. There's again and again, there are disasters, oil spilling disasters from oil platforms when something has happened to their drilling structures. Yeah. But you're right. I mean, these images, there are also many, many examples where you see actually ships spilling oil, and then you can detect the ship driving away, and you see the oil spill behind the ship. So same thing, but this bright returns here, and they all look very similar. They come from oil platforms. Okay, any other questions? Okay, thank you, Priya. Then I would still say I think 8 minutes is maybe enough just to refresh a bit, and we'll be back here at 1:15. Thank you. So, okay, we come to the last part. And just quickly see. Okay. So now this is the part for the next 45 minutes. Okay. And well, these are things we have. No, that's what we're looking at. Okay, first, okay, we'll put my hair here in order, and then we talk about the graph. So there are some geometric issues you have to remember when we now talk about the images. Okay, one I have mentioned before, the radar always looks to the side. So the nadir, which is different to optical systems, the nadir point is below the SAR sensor, but the SAR looks with a certain look angle of that sub-satellite track, either to the right or to the left. So east looking or west looking, and sometimes the satellites even are being turned around, so to look to the other side. Well, especially for you, just to remember, it looks to the side. So the image starts somewhere, some kilometers away. So the image, also called the swath, starts being away from the nadir point. So the explanation is that the radar image is being constructed by the time the signals need from the sensor to the surface and back. So the range. And we also call this the range direction or the range resolution, cross track or range direction. So because we are emitting these pulses, the radar pulses, and to locate from where the pulse was backscattered depends on the time the signal needs. So we know velocity of light is our constant, and so we can determine by the time the signal needed from the sensor to the surface and back, we can determine the range, the direction. So I mean, it's the same principle that is being used by altimeters or by LiDAR, from the time that the signal takes. So the closer the signals are to the nadir point, the more difficult it would get to discriminate between the different returns, because the distance are also similar. So you have to have a certain look angle where you can start discriminating, because I mean, these would be pixel by pixel by pixel, where that radar pulse actually comes from. So that's the reason why we have to look to the side. So, and again, I mean, this was one of the advantages for the military, flying along a border and looking into another country, but not having to fly on the territory of another country. So you're flying along the border. So, but the reason why this is like this is because of the engineering physics behind. You need to have that offset to be able to discriminate different returning times, the ranges. Okay, that is one. So the range direction. And the other one is the azimuth direction, a long track of the satellite's path. So if our radar sensor is the flight direction, it's flying like this, then you see, I mean, this would be the illuminated radar area. So while the satellite now flies, and that's similar to optical systems, of course, with flying over the area, one of these, what we call the radar looks, one radar look after the other is being put together to form the radar image. So here that rectangle would be the radar image eventually. And so we have a swath width like in optical images. Now we have a range direction. We call it range because the location is calculated by the time the signal needs, and we have an azimuth, a long track direction, and flight direction. Okay, so please remember range direction, azimuth direction. Yeah, because now we have a very special feature, and that is now the basis for the synthetic aperture radar. Okay, if we have so this is supposed to show the antenna, and that would be what we call the real aperture. So one real antenna on an airplane or in space looks to the side. And now we're looking here at the width of this antenna look. Yeah, what we have seen here, yeah, this is like an egg shape, but in reality, of course, yeah, these are wave fronts being emitted, so it's spreading out. Why it's not spreading here has already to do something with this technique called synthetic aperture radar, the SAR technique. So really, one antenna look would be wave fronts, yeah, that extend and extend even further, what is shown here. So they extend and extend and extend. So what this means that here, what we would call near range, because it's near to the sensor, here would be the nadir line, near to the sensor. The resolution, meaning the area that is covered by one radar pulse, by one wave front being emitted, would be smaller. Here's for one, and just an object D1 that would be hit here by a wave of this size in azimuth. But if we go to far range, here is another object. But you see now how far this antenna beam, so the beam width, the waves, how far they spread out. So the resolution here at the far end, would be very, very poor. There would be this whole area here covered by this one antenna loop would only give one return because of the wave front geometry. So here you would not be able to distinguish that object. So synthetic aperture, that is an idea that was developed in the 50s and 60s and then published in the 70s. Yeah, so it's not so old because it includes a lot of processing. The idea is that here this object is already being observed when the antenna is here. It first is being hit here from this position. And while the antenna is flying along in azimuth, along the satellite track, it will contain backscattered signals from this place again and again and again and again. And at this position, this is the last position where a backscatter from this point would be included in that signal. So synthetic aperture now has the idea that, as a train that passes you by, if the train would emit a sound, if the train would emit a sound, then when the train comes to you, when it approaches you, the sound gets higher and higher and higher, and only when the train is closest to you, you indeed hear that frequency of that tone. And if the train disappears, the frequency gets lower because the train is traveling with its sound, so the tone gets lower. And this phenomena is called the Doppler phenomena. So here we have the same thing. We have one frequency being emitted, but the backscatter that comes from this point, as long as the instrument approaches the point, so as long as the instrument approaches the point, the backscattered signals of that frequency change according to the velocity of the satellite. So the frequency increases until at this point, the backscatter indeed has the frequency that has been emitted, And when the satellite flies by, now the frequency is getting decreased because the sensor flies with the emission direction of the backscattering direction of that signal. It's like a little, you throw a stone in a pond and circles are being formed, and you put in a little ship, a toy ship, and as long as the ship approaches that center that is emitting these little waves, it has to cross many little waves, and when it moves away from that stone or from that center, that where the stone has caused all the little waves, and if the ship moves away from that center, then it will travel with the waves, and so the amount of waves it has to conquer will be less. It's a simple idea coming from electromagnetics, but you can imagine to process all the covered area is quite complicated. So, 30 years ago, when I worked at the German Aerospace Center, to do this kind of processing, image processing in range and in azimuth, this synthetic aperture processing, took for one small scene, an airborne scene, it took 24 hours. 24 hours for a very small scene. It's a lot of calculating. Now, I think the commercial systems, if you get a satellite image, it's maybe 20 minutes for a much larger area. So, of course, computing has advanced, but it is a complex process. So, I mean, that's all you really need to know here about the image geometry for now. Now we have a range direction that is calculated from the time of the signal. And we have an azimuth direction that is calculated here, as we see from the width of that antenna beam. And this would be a very bad geometric resolution if we could not apply the synthetic aperture processing based on the idea of the Doppler frequency. So to follow the backscattered signals as long as we observe a certain point. Okay, so there's a lot of material on this, of course, in the background, but for geoscientific applications, it's just enough. It's for you to understand there are different range and azimuth resolution that form the image. Okay, is side looking really necessary? I try to explain. Here's a little video that you can use. Okay, now we look a little bit deeper into the image formation, image geometry. Well, this is didactically not so nice, but here the radar flies now in this direction, so azimuth is in this direction. This is the illuminated ground, and just if you have wondered, so how does this work with a slant, with a range direction? Okay, there is a magic term here, the PRF, the pulse repetition frequency, which means how often are radar pulses emitted, and you see, depending on the sensor, it is between 1,000 and 4,000 hertz. So 1,000 to 4,000 times a second, these pulses are emitted. So yeah, if you just imagine, I mean, here, yeah, we are talking, and of course, this is, since we are using the velocity of light as reference, yeah, we're using the velocity of light as reference in this range direction. Well, this, let's say, this is an adequate sampling amount, 1,000 to 4,000 per second, and this is many times faster than the velocity of flight of a satellite or even an airplane, but even also a satellite that flies 7 kilometers per second along its track. So the radar still moves, relatively speaking, slow enough that these signals that are being emitted here with the velocity of light and 1,000 or 4,000 times a second, we get enough signals coming back from the certain area to be sure that we are connecting the right signal with the right place on the ground, which is forming our pixels later in the image. Okay, so this is because PRF is one of the parameters that at some sensors you can choose them. And logically, the higher that pulse repetition, the more pulses you generate and return, so your spatial resolution gets higher. So this is why we introduce the term here later. If you want to use radar images, you can look that up, just to understand what the pulse repetition frequency implies. Just another SAR image of a place in Germany, Karlsruhe, also place of a famous technical university. And as a matter of fact, the university where Hertz has developed and worked. So when we talk about the frequency, the hertz, the gigahertz, it goes back to this scientist who has worked here 200 years ago. And it's also the home of one of the very good photogrammetry institutions. And by the way, I have worked here also as just a young master student. When I finished my master, I was working here in this building for a year, or 1.5 years. With photogrammetrists. Okay, but again, here we're looking at a very high geometric resolution, where you identify all these individual trees even. So now you see is from some of the buildings, you get strong returns. I'm just looking whether you see anywhere a star-like, but you see these, what we've seen before. You have sometimes looks like a stripe that is either in this direction or here. This is maybe like a star in this, so in the vertical and horizontal. So these lines, that they originate from processing, from the range and azimuth processing. So that is why you have sometimes these features, especially in very high resolution images. So now you can understand where these artifacts in the image come from. So other than that, we see again the radar looked here from top, and we have radar shadows behind. There's nothing more to say to this image. Because we want to come to the geometrical effects in the image, and this is important that you understand them, because of the side-looking geometry, we have funny effects in images where we have topography, and obviously we have a lot of topography on our planet, so we have to deal with that problem. Okay, let's look at that image. This is in German, but there's no big surprises here. We have our radar sensor. It looks to the side, with a certain incidence angle. Okay, and now it has been emitting these wave fronts, in German Wellenfront, wave fronts. Okay, so what is happening here? Now look at that. We have to determine where the signal comes from by the range, so by the time the signal needs. Okay, and here we have a problem because in near range, so near to the nadir track, the signal from the top of the mountain returns earlier than the signals here from that slope. And as a matter of fact, the backscatter from this point would come back in the same time like that signal here from the foot of the mountain. Yeah, so this is indicated here that if this is now our slant range image here, this would be the image and the position of that backscattering, then in our image, we would have the top of the mountain first, and then the foot of the mountain, of that slope facing the antenna, and it's actually temporally at the same location as this point. So I is K and J equals L, because it would also be on the same temporal distance, on the same range with that point on the ground. So here we have a problem. Okay, then we touch here the back slope. So H is H of the slant range image, that's fine. Here we get another type of problem. Here the whole slope would be on one distance, one signal, meaning the top of the mountain and the foot of the mountain slope would be equal temporally, same distance, same range to the sensor. Okay, and then we come to a phenomenon in far range. Here we are far away from the nadir line, in far range. Okay, now we hit the foot first, which is nice. Okay, then the temporal distance to the top of the mountain is very, very small. Okay, but now we are looking with such an angle that we indeed have that radar shadow. And we cannot see what is the type of slope or vegetation or land cover in this part, because we have no signals. It's the radar shadow. Okay, these three phenomena, they are geometrically very easy. Yeah, you can always remember this graph. It's very easy to understand, but it's of course a big problem. So they have three names. This first name is the so-called layover. It's layover because the top of the mountain is being represented first. So it's laid over, and then come all the other signals following here on the slope. Layover. That's the first bad geometric problem. The second one is called foreshortening. Foreshortening. Because here the whole slope is only one signal. So it's shortened, in this case, to the extreme. The return of the top is the same from the slope, foreshortening. And the radar shadow, you already know, that's the most intuitive. These two are not very intuitive. But if you look at this little graph, it's just clear what happens. Now, how do we get out of this problem? If you know the height of the sensor, which you always know, airborne, satellite-borne, if you know the geometry, if you know with which look angle your image was constructed, then you can actually reconstruct these problems if you have a digital elevation model. So that's why digital elevation models are so important. I mean, for all kinds of applications, also for optical remote sensing, and of course, all kinds of infrastructure, mobile communication planning, all kinds of things. But for radar, it is absolutely crucial. It's the go, no-go decision. If you have no digital elevation model, you cannot retrieve, explain, recover, correct this funny geometry. In an optical image, if you have no elevation model, you have your sensor looking in nadir, you have a sun illumination, you have illumination effects also. Yeah, the sunlit side, the shadowed side, you have to correct. Also in an optical image for radiometric effects. But you do not have strange geometries like you have in radar images. But the strange geometries, again, it is very, very easy to correct if you have a digital elevation model. But there's one more. Now you can see here, also here. I mean, this is really funny. Yeah? If you first get the signal from the top and then the slope is being covered, you can reconstruct the geometry, but you cannot reconstruct the backscatter. This is much too difficult to just turn things around here. Also, if you have foreshortening, it really gets bad. It's only one signal from the whole slope, which you also cannot reconstruct. You cannot recover because there is nothing to recover. It's one signal from the whole slope. So geometrically, you can correct, but radiometrically, you don't know what's happening. So again, with radar, you need to look from both sides and, if possible, from different observation angles. So then, I mean, you have to have your master geometry to which you correct all your images. But when you have steep terrain, and then you have to reconstruct all these backscatter information from the different slopes. So radar in high relieved areas, in lots of topography, it's not impossible to solve, but it takes some more pre-processing steps. Okay. Yeah, so that is really important that you understand what's happening here. Okay, let's go through some of the slides and examples, but maybe if there is any question at this point, please speak up because this is absolutely important. Okay, so you seem to either you all know that all or you understood. Now we move. Some examples. Here is one, Mojave Desert. Now here you see very nicely, okay, here the whole slope is one line. Yeah, the whole slope is very bright in one line. So this is all foreshortening, all foreshortening. And here we are becoming an expert. You can already see, there are some peaks. Yeah, there are some peaks coming out of it that I can detect. And this is actually layover, the same here too. There you see the peaks and a bright return layover. This is another example. This is from the Alps somewhere. Okay. Yeah, and here you see very nicely these bright returns, and here you see peaks kind of projected on the next slope. This is all layover. This is all the returns coming first from the mountain peak and then walking up that slope that is facing to the radar sensor. Same thing here. That's all layover also here. These lines here, this may be, well, probably not layover anymore. This is foreshortening. This is the whole slope. The slope on the other side of that mountain is probably as long as this one, facing away from the radar antenna. But it's all compressed to one line. Same here. So it makes the, I mean, you see the surface in a very plastic way, very each topographic feature is almost being enhanced, but the geometry is absolutely corrupted. So two things. One is about the first 10 years of radar remote sensing were governed by the two satellites ERS-1, here it is again, ERS-1 being launched in 1991, and ERS-2. They both lived until the turn of the millennium, so around 2000. A little bit shorter ERS-1. So, but these years, the 90s, 1990s, were governed by the exploration of ERS-1 and 2, also for biomass with some nice projects that brought me to Krasnoyarsk in the 90s. So ERS1 and 2 had one major disadvantage for topographic areas. They had a fixed incidence angle of 23 degrees. So very steep. And if you go back to this image, so 23 degrees is quite a steep incidence angle. And well, these satellites in the 90s, they have been defined by oceanographers. Nobody really expected much use of radar on land. It was determined by the European oceanographers to use C-band wavelength because they thought it's a good wavelength for all the roughnesses on the ocean surface. And to be more sensitive to the roughness, they wanted a steep incidence angle. So they looked with 23 degrees, and because of the technology at that time, it had only a very small range of angles that were covered. So it was only about, I think, 1.5 degrees in either direction. So 23 degrees was the central incidence angle, plus a little bit to both sides. And you see from this little graph, the closer you go to near range, the bigger gets this problem with the layover. So you can always say in near range, you get the problem of layover. If you walk then towards far range, you get a problem of foreshortening. And at the end, you have the problem with the radar shadow. So also from this little sketch, you can easily remember. Okay, so with ERS1, we had almost everywhere on this planet where we have topography, major problems with these geometric artifacts. So just as a remark, for 10 years of radar remote sensing with ERS1 and 2 under very steep incidence angles, just to be careful, because you have beautiful mountains in Russia. Okay, and then just another little remark here on the difference between slant range and ground range. So if you get one of the formats you are using is a geocoded ellipsoid corrected image, GEC, geocoded ellipsoid corrected image. And that is nothing else than a transformation here from the slant range, which collects your pixels by time. Just using an angular correction to the ground range, now transforming A, B, and C to a flat Earth, It's not correct. And a GEC, a ground range, a geocoded ground range image is not being corrected for terrain. This would be then a GTC, geocoded terrain corrected. But for this, you always need a digital elevation model. Okay, these are just some little geometries for the users. This is the foreshortening, and here so we have the layover. Okay, so if you have a digital elevation model, you can correct such areas as has been done here. So what you do is you stretch that slope to the real locations. And what has to be considered is that, of course, you do not have valid backscatter information on that side. So you either have to just stretch it, fill it in with values from, with backscatter values from in between. And if you want to assign a height to these areas, then you do need to look from the other viewing direction. Okay, and yeah, this is already, didn't read this. This is a simulated ERS image. So how is this correction process done? Well, if you do have a digital terrain model, as I have said before, and then go back to our introductory graph, Yeah, if you do have the elevation model, you have the height, you have the look angle, you can actually simulate the distortions. And so this is what this example here shows. This is the real image, and this is the simulated ERS image. You can simulate this viewing geometry, and then the next step is what you do is you co-register your strange geometry radar image to the simulated radar geometry, and from that you can kind of unroll and correct for the geometric features. But it's only possible if you have an elevation model. Okay, radar shadow. I think this same principle. Again, you need an elevation model and the height and the angle of your radar sensor. Then you can calculate where the shadow would occur, and you can correct it geometrically. But again, that information, there is no information to be recovered radiometrically from the backscatter information. Okay, I think it's really, I mean, it is a disturbing fact, but I hope I could show you that this can be corrected. And with this, we would move on to the last 10 minutes, to the last part of this lecture on the SAR backscatter and speckle. And I think much of it. So any questions here at this point? Okay. Okay, I think as many of this I have already said, so we can move on more quickly. Okay, amplitude I have introduced in the first part. And well, there is another concept you have to know, the normalized radar cross-section, or the so-called backscattering coefficient. That's how we call it in radar remote sensing. And what is this? It's abbreviated with a sigma, and then we also call it sigma naught, because the naught stands for the a calibrated signal for the instantaneous field of view. So with respect to the geometry of that specific sensor. And so sigma naught is our calibrated radar signal that comes out from the radar equation, and the radar equation includes this ratio. I have to be careful here because it says something else. It first starts with how much energy is being emitted. So the power that is being sent out by the antenna. Then the radar equation also includes the so-called antenna gain. Now, what are the technical characteristics? But we don't have to deal with these technical parameters, because that is being delivered by the space agencies. So each of our signals goes through goes through technical calibration equations, so that at the end we have an image that is considered by these sigma naught values, which I can compare. If it is a C-band signal, I can compare it whether it's taken by airborne or spaceborne, or maybe some handheld signals on the ground. I can compare it over time, so it's easy to construct time series, because radar is so independent of atmospheric effects. So every calibrated radar signal